Chapter 12, Introduction to Analysis of Variance, Part 2. The test statistic for ANOVA is very similar to the independent measures t-test used in Chapter 10. For the t-statistic, we first computed the standard error, which measures how much difference is expected between two sample means if there is no treatment effect, that is, if the null is true. Then we computed the t-statistic with the following structure. So t is equal to the obtained difference between two sample means divided by the standard error, which represents the difference expected with no treatment effect. And this is translated into the following. We took sample mean 1 minus sample mean 2, and then subtracted the population mean 1 minus population mean 2, again that was representative of the null, which indicated that mean difference would equal 0, over the estimated standard error of the mean difference. Now it's important to focus on the fact that we are computing the difference between two sample means, and this structure only allows us to compute the difference between two sample means. For analysis of variance, however, we want to compute differences among two or more sample means. With more than two samples, the concept of difference between sample means becomes quite difficult to define or measure. For example, it would be if we had, let's say, 3 sample means. So it would be sample mean 1 minus sample mean 2. And then if we have a third one, well then we would perhaps have to say sample 1 minus sample 3 and sample 2 minus sample 3. So you get the picture. It becomes very convoluted if we try to compute the mean difference when we have 3 or more sample means to compare. So again, the structure of the t-test no longer works because it is focusing on the mean difference. Another example would be if perhaps we have one sample mean equal to 20 and a second sample mean equal to 30. So when we just have two, the mean difference is quite easy to calculate. We would indicate that there's a 10-point difference between these two means. But let's say we add a third mean of 35. And again, this should illustrate that it becomes problematic to compute the mean difference when we add one more sample mean. Again, we could have a fourth sample mean. So again, we recognize that this concept of mean difference is no longer applicable once we add an additional mean. So the t structure is limited to two values. And in fact, if we reflect back on Chapter 9, which is the t-test for a single sample mean, the numerator of the equation was m minus mu. For the t-test for independent sample means is illustrated here, where we take sample mean 1 minus sample mean 2. And in the final Chapter 11, we had the mean difference minus the hypothesized mean difference. So again, recognizing that we have two values in which we are computing a difference between. And again, if we add at minimum one more sample mean, then this process is no longer applicable in determining the differences between conditions that we are testing. An alternative or solution to this is that we can now use variance to measure the sample mean difference when there are two or more samples. The test statistic for ANOVA uses this fact to compute an F ratio with the following structure. So our new statistic is referred to as the F ratio, and it's equal to the variance between samples. And again, when I use the word, or we use the word variance, you can interpret that as differences or variation. So I'll use those terms interchangeably. So again, variance is representative of the difference between the values in the distribution, or also represents the variation we see between scores in a distribution. So again, the F ratio is computed by taking the variance between sample means over the variance expected with no treatment effect. And I'll go into specifics as to which of what those two variables represent and how they would be computed. So before I go into the specifics of what is represented by the numerator and the denominator, let's just review quickly that the test statistic for ANOVA, it does not allow us to compute a sample mean difference between more than two samples. Again, we saw that mathematically it's impossible to compute the mean difference once we add a third or fourth or fifth sample mean to the study, and difference of means is no longer possible. So the F ratio is based on the variance. Again, variance meaning the variation, the difference, instead of the sample mean difference. And variance used to define and measure the size of difference among the sample means is represented in the numerator. The variance in the denominator measures the mean difference that would be expected if there is no treatment effect. And that denominator representation is similar to the standard error. Again, the standard error is the difference we would expect between sample means if there's no treatment effect. And here we're saying it's representative of the variance between the mean differences that would be expected if there is no treatment effect. So again, the denominator given the t equation is similar to the denominator in our new F statistic. But we're going to go into details to specify exactly what is it that we're measuring in the numerator and in the denominator of our new F statistic. When we were introduced the t-test, the family of t-tests, we understood instances when we would use the single sample t-test, the t-test for independent measures t, or if we would be required to use the repeated measures t-test. Again, each of them had unique characteristics, and depending on how participants were allocated to the different conditions, whether or not we had all population parameters, dictated which t-test was most appropriate. And now with the introduction of the analysis of variance tests, we recognize that it is an advantage to conduct an analysis of variance opposed to a t-test, simply because it allows us to compare more than two treatment conditions. So again, if you were to be asked a question on a test as to why we would opt to use analysis of variance opposed to a t-test, your answer would, or response would simply be that there's an advantage to computing analysis of variance because of the fact that it enables us to compare more than two conditions. So you may wonder or question, why not conduct multiple t-tests if you have more than two sample means or more than two treatment conditions that you want to compare? In other words, why can't we conduct a t-test comparing sample mean 1 and compared to sample mean 2, and sample mean 1 compared to sample mean 3, and sample mean 2 compared to sample mean 3. So that is one option, and again, this would result in 3 hypothesis tests, 3 tests, 3 t-tests to be more precise, and that is one approach. However, the downside of that is related to the potential of committing a type 1. Remember that each time you do a hypothesis test, you set an alpha level to determine the risk of type 1 error. If we were to use alpha equal to 0.05, for example, there is a 5% or 1 in 20 risk of a type 1 error. And so if we can think of that again, and we recognize that our alpha level set determines the probability of committing a type 1. So let's say alpha is equal to 0.05. Again, that would leave 0.95% of the distribution in the center, and the 0.05 would be split amongst the two tails. And if we perform the test of mean 1 and 2, again, alpha set at 0.05, again, we only have a 5% chance of committing a type 1 error. However, if we perform that test 3 times over, again, we're comparing the mean difference between what we illustrated here, we would have to conduct 3 different tests. And as a result, the alpha level would be affected by that, and consequently the potential of committing type 1 error would be inflated. So researchers make a distinction between what they refer to as test-wise alpha and experiment-wise alpha. The test-wise alpha level is simply the alpha level that you select for each individual hypothesis test, for example, alpha equal to 0.05. The experiment-wise alpha is the total probability of committing a type 1 error and is accumulated from all the separate tests in the experiment. Mathematically speaking, the experiment-wise alpha would be computed by taking 1 minus our alpha cubed if we have three separate means that we are comparing. And again, this total is 1, right? And maybe perhaps if I write 1.00, that will make a little more sense. 1.00 minus alpha to the third power. So if we just compute what's in the parentheses here, given the scenario of alpha equal to 0.05, then we would calculate 1 minus, and 1 minus alpha is the 0.95. We would cube that, and now in our calculators, 1.00, again, it's 1 representing the entire proportion, or 100% of the distribution, minus 0.95 cubed in our calculators is equal to 0.857 if we round. And now if we take 1 minus 0.857, what we're calculating is the overall experiment-wise alpha if we were to perform 3 separate hypothesis tests. And that would equal, again, what we're solving for, and I apologize for not being precise, is experimenter-wise alpha is equal to, and now experiment-wise alpha is equal to approximately 0.14. And now what we've just concluded and what we just calculated, that if we do these 3 separate tests, the potential of committing a type 1 error goes from 0.05 or 5% to 0.14 or 14% probability. And so again, if we do these 3 separate tests, that inflates the potential of committing a type 1 error. The calculations that I just performed here is not something that you would be required to do, but it is helpful to understand why we would opt to use an analysis of variance opposed to separate t-tests. Again, the reason being that conducting 3 different tests is going to inflate our alpha level, excuse me, not our alpha level, but will inflate the potential of committing a type 1 error. And again, that's mathematically shown here by what I just computed. So again, by just computing 1 test, for performing 1 hypothesis test with alpha at 5%, the risk of committing type 1 error is 5%. But now if we do it 3 times over, that increases significantly to now 14% probability of committing a type 1 error. When we conduct analysis of variance hypothesis tests, that alpha level remains the same. In other words, there's no difference between the test-wise alpha and the experiment-wise alpha, because the test is all done simultaneously and we don't need to do separate tests. So if we go over this very last point here, ANOVA, or analysis of variance, evaluates all mean differences simultaneously with 1 test, regardless of the number of means, and thereby avoids the problem of inflated experiment-wise alpha, as I just demonstrated here mathematically of how to compute our experiment-wise alpha. So going back to our F statistic equation, again, F is equal to the variance or differences between sample means over the variance expected with no treatment effect. So I'm going to give you an example of exactly what these variables represent and how we can express them verbally. The formulas and calculations required in ANOVA are somewhat complicated, but the logic underlines the whole procedure is fairly straightforward. Therefore, let's use Table 12.1 to introduce this logic behind the analysis of variance, or ANOVA. The data represent the results of an independent measures experiment comparing performance in a driving simulator under 3 telephone conditions. Again, the factor here for the analysis of variance would be the telephone condition. Again, in the past we've expressed it as the independent variable with different conditions, and now with analysis of variance we would refer to as the factor, and the levels are no phone, handheld phone, and hands-free phone. And the dependent variable is the performance in the driving test that's administered. So let's analyze and look at this data. One obvious characteristic of the data in this table is that the scores are not all the same. In everyday language, the scores are different. Again, the word difference can be also interchanged with varied or variance. In statistical terms, the scores are variable, again, meaning that they're not the same, they are different. Our goal is to measure the amount of variability, or in other words, the size of differences, and to explain why these scores are different. Again, the explanation can be one, it's just due to unsystematic random factors, also known as chance or sampling error, or the alternative is that the scores are different because of the treatment administered to these 3 different samples. The first step is to determine the total variability for the entire set of data. To compute the total variability, we combine all of the scores from all of the separate samples to obtain one general measure of variability for the complete experiment. Once we have measured the total variability, we can begin to break it apart into separate components. The word analysis means dividing into smaller parts. Because we're going to analyze variability, the process is called analysis of variance. This analysis the analysis process divides the total variability into 2 basic components. The components are between treatment variance and within treatment variance. So looking at the data in this table, we clearly see that much of the variability in the scores results from general differences between treatment conditions. For example, the scores in the no phone condition tend to be much higher, with a mean equal to 4, than the scores in the handheld condition, which is the mean equal to 1. And also the hands-free phone condition, which is a mean equal to 1. We calculate the variance between treatments to provide a measure of their overall differences between, again, the key word there is between treatment conditions. Notice that the variance between treatment is really measuring the difference between sample means. So when we talk about between treatment variance, we're talking about the difference between here and here and here and, here and there and there and there. So again, between the conditions, we want to know how much variation exists between these conditions. The within treatment variance, in general, is representative of the differences that we see within each sample. So again, notice that we're administering this treatment to 5 different individuals in treatment 1. And I'll ask you, are all of these scores equal to one another? And your answer should be, no, they are not. They vary, they differ from one another. So we want to account for what we refer to as within treatment variance. Again, within each sample, the scores vary or differ from one another. So we explain that within treatment variance as resulting from unsystematic random factors. Again, we have no control over the characteristics that these participants bring to the table with them, but those characteristics, or what makes them who they are, has implications for the dependent variable that we're measuring. So again, we see that there is variation within the samples, and that is explained to unsystematic random factors. Again, it's just due to the makeup of the participants. and we recognize those variations will exist, but our emphasis really is on the differences between the conditions than the differences within. And we'll talk again about mathematically how those values are in a sense canceled out once we look at the equation that we are computing for F statistic. So again, we have between treatment variation, and we have within treatment variation. So again, the between is looking at the differences between these sample means, and the within is simply looking at the differences, different scores that we see within each treatment. So again, we note that 4 is different from 3 and 3 is different from 6, so on and so forth. So again, the within opposed to the between. So those are the concepts that we're going to focus on. So to review, the between treatment variance represents variability that results from general differences between the treatment conditions, and variance between treatments measures differences among sample means. And then we learned about within treatment variance, which represents variability within each sample. Individual scores are not the same within each sample. So again, we see that within each treatment, the scores are going to differ, and we refer to that as within variance or within treatment variance. And then when we're comparing one condition to the other conditions, we refer to that variation as between treatment variance. So sources of variability between treatments. So the sources include systematic differences caused by treatments, and again, that's our interest, as well as random unsystematic differences or the individual differences that we see within. In other words, the between variance includes the systematic differences or the treatment effect, as well as what was represented as the within treatment variance. And in a subsequent slide, this will probably make more sense, but for now, just understand that the between treatment variability or variance encompasses both the treatment effect as well as the unsystematic differences, or what we refer to as individual differences that are not as a result of the treatment, but simply a factor or function of the differences between individuals or the participants and the characteristics that they bring to the study, and that are not reflective of the treatment that they were exposed to. So sources that explain the variation within treatments. So we explain that as, or express it as, no systematic differences related to treatment groups or within each group. And we can also indicate those to be random and unsystematic differences. Again, those individual differences. What makes you, you is going to be different from what the characteristics that make me who I am, and also have implications of how I will drive given these different conditions that we talked about in table 12.1 when we're looking at different phone conditions in relation to driving performance. So again, the within treatment sources of variation can be accounted for by random unsystematic differences, which we can equate to differences among individuals. So if we break down this F ratio, we can think of it as the numerator represent differences including any treatment effects over differences with no treatment effects. Again, the things that make those scores different are things that are outside of the treatment and can be related more to the differences that individuals bring to the table when they participate in a research. Figure 12.3 shows the overall ANOVA and identifies the sources of variability that are measured by each of the two basic components we just discussed. So again, we have total variability, and total variability is comprised of two different variances. One referred to as between treatment variance. Again, variance can be interchanged with the word differences. And within treatment variance, or differences. So the between treatment variance is a function of these two things, or the causes of variation are one, systematic treatment effects, again, that the treatments cause a difference in scores, and also the random unsystematic factors, which is another way of saying the within treatment variance. So it includes treatment effect and what we refer to or define as within treatment variance. The within treatment variance is explained by random unsystematic factors. Again, we see within one condition, everyone's score is going to be slightly different from the other scores. And those differences are as a result of random unsystematic factors, not due to treatment, because again, it's within the treatment. And between encompasses both things, the treatment effect as well as what we refer to as within variance. So if we look at our F ratio, again, it's between treatment variance, which includes these two concepts here, systematic treatment effects and random unsystematic factors, over within treatment variance. So again, if I partition this out, we're talking about treatment effect and within treatment variance. So again, it encompasses both those things, that we see differences between the conditions, one, because we're assuming there's some effect due to treatment, and two, because the scores have variation to begin with. Those participants are going to produce different scores, which results in variation or differences. So if we think of this mathematically, if this value, right, part of what makes the numerator and is contributing to the between treatment effects is equal to what we see in the denominator, if we see treatment effects, again, these, or regardless if we do or if we don't, these essentially will cancel each other out, and what we'll end up with is a measurement of the treatment effects that we're measuring or that we're testing or are interested in. So this is a good way verbally to understand what the F ratio is expressing. Again, we're taking the numerator, which is reflective of variation based on two sources, treatment and random unsystematic factors, and the numerator is comprised of simply random unsystematic factors. In the end, our interest lies in the differences between the treatment conditions. So if those two values cancel each other out, whatever's left over is representative of the variation that is explained between the groups that we're testing. And when I say that they cancel out, I'm not necessarily saying that they're equal to 0. What I mean is that if I take one value and divide by the equivalent value, let's say 5 divided by 5, what would that equal? It would equal 1. So again, when I say they cancel each other out, I'm not implying that that would equal 0. But let's consider a scenario of what our F statistic would look like if we detected 0 between treatment effect. So let's consider a scenario where we detected 0 differences between conditions. So again, the numerator represents between treatment variation and consists of these two causes of differences. One is the treatment effect and the other is random unsystematic factors. So let's say the first one, the treatment effect, was equal to 0. So we enter 0 here in the numerator, and then we add the random unsystematic factors, also known as within. So again, number 1 is 0, and the second contributor to that variation is referred to as the random unsystematic factors. And then the denominator is the within treatment variation, which is the same as random unsystematic factors. So let's just make up numbers and say that mathematically speaking, we'll learn how to compute all of these different variables in a subsequent video. But for now, just focusing on the basics, if there is 0 treatment effect, and let's say numerically speaking, the random unsystematic factors was equal to 5. So that would be represented in the denominator as well. So 0 plus 5 is equal to 5, and divide by 5, and we get an F ratio equal to 1. So an F ratio equal to 1 or near 1 indicates that the differences between treatments, the numerator, are random and unsystematic, just like the differences in the denominator. With an F ratio near 1, we conclude that there is no evidence to suggest that the treatment has any effect. And I'll briefly show you the F distribution, which is positively skewed. And in the center is representative of the null hypothesis and an F ratio equal to 1, right? Because if the differences are simply due to random unsystematic factors, then if we take one divide by the other, and if they're equivalent to one another, then the ratio would equal 1. And again, given this positively skewed distribution, this 1 is representative of the null. No treatment effect, no difference between conditions. And that's what we see here if, again, the first contributor to variance for between treatments is equal to 0, then given that scenario, and we take the random unsystematic factors, divide them by the same variable, the random unsystematic factors known as within treatment variation, then we have a F statistic equal to 1. When the treatment does have an effect causing systematic differences between samples, and the combination of the systematic and random differences in the numerator should be larger than the number or the random differences alone in the denominator. So for example, let's say instead of seeing 0, a numeric value of 0 representing the systematic treatment effects, let's say, for example, we calculated a number equal to 10. And again, we'll still use the 5 as representing the random unsystematic factors. Again, they would be equal when we look at the numerator and the denominator. So now instead, let's say this is now equal to 10. And our new F ratio is equal to 15 over 5, and we get an F ratio equal to 3. So that would be somewhere, over here, 3.00. And this should give you a good sense as to why the distribution is positively skewed. Because if we have systematic treatment effects, the numerator will always be larger than the denominator, so it always produce a positive number, which is why we're going to focus on the right side if we want to reject the null hypothesis. Any F statistic that's around 1 or equal to 1 indicates no treatment effect. There's no differences between groups. Anything that deviates from 1 and further out into the tail is going to suggest that we see some treatment effects, and then it's our job to determine if that difference is statistically significant using a critical F that we'll learn how to compute and identify. So if the null is true, the size of treatment effect is near 0, F will be near 1.0. So again, we were saying that between treatment effect is representing the treatment effect plus the random unsystematic factors. So if the treatment effect is somewhere near 0, then our F ratio is going to be computed to equal something near 1, because again, this random unsystematic factors is equal to the within. So if we take one value and divide it by itself, it's going to give us something close to 1. And again, that's only if the treatment effect is 0 or something close to 0. If the alternative is true, the size of treatment effect is going to be greater than 0. And again, we would take the treatment effect plus the unsystematic factors, which would always produce a numerator that's larger than the denominator. So our F will be noticeably larger than 1. And the denominator, the F ratio, is called the error term. And the error term provides a measure of the variance caused by random unsystematic differences. So again, when the treatment effect is 0, null is true. The error term measures the same source of variance as the numerator, the F ratio. So the value of the F ratio is expected to be nearly equal to 1. And I know that this is a bit overwhelming and there's a lot to take into consideration, but it's good to start with the verbal interpretation of the variables in the F ratio before we start moving into the equations of how to compute the between treatment variation versus the within treatment variation. But again, when it comes down to drawing our conclusions, opposed to what we've seen in the past where the t distribution showed no treatment effect equaling 0 in the center of the distribution, now we're working with a skewed distribution where we would take this ratio, and if it's near 1, we're saying that there's 0 to or little treatment effect, and if it deviates from 1 on the positive side, always on the positive, because the numerator will always be greater than the denominator if we do detect any treatment effect, any differences between conditions, then we will be able to reject the null, but again, it's going to be based on our critical F value that we'll learn how to identify in a subsequent video. So I would recommend that you take a look at some YouTube videos that I posted that I found to be a very great visual illustration of this total variability and broken down into the components of between treatment variation and within treatment variation. So take a moment to look at those in addition to all of the videos that I will produce and post for Chapter 12. So we'll end this video, this lecture video, with a learning check, and we'll decide if these following statements are true or false. So first, ANOVA allows researchers to compare several treatment conditions without conducting several hypothesis tests. True or false? And the answer to this is true. We discussed at the beginning of this video that the advantage of conducting analysis of variance is that it enables us to compare multiple treatment conditions without the potential of increasing the likelihood of engaging in a type 1 error. So that inflated probability of engaging in type 1 error is a function of producing separate or conducting separate tests. So analysis of variance enables us to conduct one test and have one alpha level, which also is reflective of the probability of engaging in type 1 error. So this is a true statement. Next one, if the null hypothesis is true, the F ratio for analysis of variance is expected on average to have a value of 0. And that is a false statement because we just discussed the null, right? If there's no treatment effect, the null would indicate that our F ratio is equal to 1.00, not 0. The 0 would be reflective of 0 differences between groups, but we still have those other variables of within treatment variation, which is also referred to as random unsystematic factors. So again, we wouldn't anticipate our F statistic to equal 0, we would anticipate it to equal 1. And that concludes part 2 of Chapter 12.